when we talk about arc length, what you're doing basically is, for example, on page 333, figure 639, if you have a function which graphs as a crazy curve, doesn't matter, on page 333, figure 639, what you can do is you can put points, and these are just x, y coordinate points on this graph, and in between any of those points, you can find the length of the arc. And using the formula that's on your formulas page listed as arc length, I think it's on your pages L. L is the notation that they use for arc length, and that's the one that we're going to use tonight. So, if you look at example number 1 on page 335, or if you even go back to the left and it picks back up with that curve, you can see that it has a straight line drawn from q sub k minus 1 to q sub k. Well, what this integration is going to do is it's going to allow us to get closer and closer with those straight lines until eventually you're at point to point. But anyway, example number 1, if you look at that, in particular the picture of figure 6.41, notice in your formula down at the bottom of page 334, it has L, which is arc length from A to B. Okay, that's the notation. You have L from A to B. That's your arc length from A to B is equal to the integral from A to B, and then you have the square root 1 plus your derivative of your function. Notice it says f prime of x. That's the notation for derivative. So you're going to take the derivative of the function given and then square it. And then you're going to integrate that. So it's a lot of algebra. It's a whole lot of algebra. But I don't think you're going to have a problem. Now, if you notice on your formulas page, you have 2 different formulas. You have a formula that is relation, or you're taking the antiderivative with respect to x. And then you have another formula that has the antiderivative with respect to y. How are you going to know which one to use? Well, I'm fixing to give you the biggest hint ever. Okay? If your function is easily solved for y, you know that y and f of x are the same thing, right? So if you can easily solve your function for y, then you're going to use that top formula. Because that's basically telling you that you can have a function. It is a function. Because remember, if we have a function that looks like the one in your book that looks kind of like this, and then we have another function that looks kind of like this, how do you know a function is actually a function? By looking at the graph. There's a test that you can do. It's the vertical line test. With this one, I can draw a vertical line anywhere I want to, and it touches once and only once. So it's a function. So if you can take your function and solve it for y, then you're looking at a function, because that's your f of x. If, however, you cannot easily take your function and solve it for y, then this is what you're looking at, and it's not a function, because it touches one and one time. Yes. Yes. So if you cannot easily solve, or if it's not already solved for y, then you're going to use that second formula, okay? Because you're not looking at a function. So that's how you're going to know which formula to use. Am I going to use the top formula, or am I going to use the bottom formula? And it all depends on if it's a function versus not a function. If it is a function, you should be able to solve for y really easily, or y is already solved for you. Okay? If it's not a function, you're going to use that second formula. Then in that case, you would want to solve for x, and it should be easy. Okay? You should be able to solve for either y or x very easily, and in most instances, it'll be already solved for you, so you don't even have to worry about it. Okay, so if you look here, notice what's going to happen is this. The arc length of the graph of f from the points, and what's going to happen is they're going to give you 2 points. You have point A and you have point B. Well, if it's a function, you don't have to graph it. So that's a sign of relief. You don't have to graph it. Instead, what you're going to do in order to get your boundaries, if it is a function and you're going to use the top formula, your A and B are your x coordinates of your points. Okay? So this A is this A, and this B is this B. Easy enough? Okay? So what if it's not a function and I have to use the second formula? Well, f of A is the same as C, and f of B is the same as D. Okay? So, if you're doing the integral with respect to x, your boundaries are just going to be your x coordinates. If you're doing an integral with respect to y, then your y boundaries are going to be your y coordinates. Easy enough? Okay, so honestly, the hardest part about this is the algebra. And we're going to be doing some crazy algebra in these problems. But if you'll just be patient, that's the number one thing. Be patient. And if you get stuck in the algebra, just take a step back and look at it, okay? You may have to erase, you may not, I don't know. But just the main thing is just be very patient with your algebra. And of course, make sure you make legal moves with your algebra. Sometimes we just want to do some weird things, and that's just not necessary. What else do I need to say? I think that's it. Okay, so let's actually look at a problem. Find the length of the curve, and like I said again, you do not have to graph these. Find the length of the curve given by y plus 1 quantity squared is equal to x minus 4 quantity cubed from the points A is 5, 0, and B is 8, 7, 5. Or 8, 7. Where did 5 come from? Okay, so with this one, honestly, I could solve for either y or x, really and truly. But since the y has a lesser degree, I'm going to solve for y. Okay? So how do I get rid of a square? This is algebra. So you're going to square root both sides. So now what we're going to have is y plus 1. Really? That was quick. With integrity and everything, it just overloads. Okay. So you have y plus 1 is equal to, now watch what I'm going to do, okay? I have x minus 4 cubed, and instead of writing the square root symbol, I'm going to raise it to the 1/2 power. Do you see what I did? Okay. So why did I do that? Well, going back to your algebra days, if you have a power raised to a power, what do you do with those powers? Multiply. So this turns into y plus 1 is equal to x minus 4 raised to the 3/2 power. Now, of course, you got to get y by itself, so you're going to have y is equal to x minus 4 to the 3/2 power minus 1. And so you have y solve for. And remember, y and f of x are the same thing. Okay? Remember that y and f of x are the same thing. Okay, so we have y solved for. So let's look at our formula. In our formula, we know that we're going to need the derivative. So let's go ahead and knock that out, because on the formula that we're going to use here is the integral from a to b of the square root of 1 plus f prime of x squared dx. That's the formula that we're going to use. So we know that we need the derivative. So the derivative, if this is f of x, we need f prime of x. How are we going to take the derivative of x minus 4 to the 3/2 minus 1? What's the first thing you're going to have to do? Chain rule. So let's move the 3/2 down. Times what's inside. Lessen the 3/2 by 1, which is going to give me what? 1/2. Times the derivative of what's inside. What's the derivative of x minus 4? 1. So we just really don't have to worry about it, right? Anything times 1 is itself. And then the derivative of minus 1 is what? The derivative of any constant is what? 0. So that just goes away altogether. So that is your derivative. Your derivative is 3/2 times x minus 4 raised to the 1/2 power. And that's what we're going to put into this problem. So do you see all the algebra that we're going to get to do? Yay. Okay, so what are my boundaries? 5 to 8. Good. And then we're going to have 1 plus that derivative, which is 3/2 x minus 4 to the 1/2 squared. Okay? Algebraically speaking, what can we do? What's something that you want to do? One more time. I think you're right. I just couldn't hear. Okay. Well, yes. Right. But watch this. We can square 3/2, right? Because we have a product inside, basically. So we can square 3/2 also, so we'll have 9/4. And then, of course, x minus 4 to the 1/2 squared, anytime you square a square root, it goes away. So you're going to have x minus 4, right? So that looks better already, I think. Now what do you want to do, algebraically speaking? Okay, we'll distribute. That sounds good. So we'll have 1 plus 9/4 x minus 9. Next step's easy to see. What do you want to do? Yeah. 9/4 x minus 8. Okay, now, where you go from here is up to you. Algebra is funny that way. You may go one way and somebody else may go another way, but we all end up at the same place, right? So, discuss. Where do you want to go? There are a couple of options here. First of all, let's talk about this. Can you square root a sum or difference? No. You cannot take the square root of a sum or difference. We've never done that. Never. So, what? What? It'd be the same thing. You're just rewriting it. Let's actually make an algebra move. What do you want to do? You cannot. That's a group, so you can't separate them at all. Come on. We have some geniuses in here. I know y'all can figure this out. What do you want to do? Tell me something that you can do. Let's not try to separate it.
Is there like a difference of square or not?
9/4, yes, but or difference of square. No, because you don't have an x squared and x small squared. Instead of thinking about separating, let's think about consolidating. Let's think about our radical rules. Back from Math 100 or basic algebra, whatever your case may be. What if we have something like this? What happens when you take the square root of a fraction, of a fraction? What is the first thing you do? make one fraction, how will we make 9/4 x minus 8 into a fraction like what I have on the board? Close. But no. You can't just do 9x minus 8 over 4 because that 8's changing. There you go. 9x minus 32 all over 4. Common denominator, because right now the 8 has a denominator of 1. So if we change its denominator to 4, we're going to have 9x minus 32 over 4. Right? Now we can do what we did over there on the board, and we can say that we have the square root of 9x minus 32 over 2. Okay? So what am I going to do? Now, Patrick, I can take a 1/2 out. Do you see that? Do you see where the 1/2 comes from? This is a 1/2. If I pulled a 1/2 out and said 1/2 times that, would you not get that? Okay. So I'm going to take the 1/2 out front. It's a constant. It doesn't have anything to do with the x values. So that's what allows me to pull it out front. So I'm going to have 1/2 integral from 5 to 8. And then I'm going to say 9x minus 32. Now I'm going to raise it to the 1/2. Because I'm ready to integrate at this point. How do you integrate that? How do you integrate 9x minus 32 to the 1/2? Use substitution. Use substitution. What is u? What is du? But I don't need a 9 dx, I just need a dx, right? So we're going to do 1/9 du is equal to dx. What am I going to do with that 1/9? 1/2. Very good. So we're going to have 1 over 18, right? Integral from 5 to 8, u to the 1/2 du. What's going to happen when you integrate u to the 1/2? What are you going to get? U to the 3/2 divided by 3/2. But I don't like that. I don't like dealing with complex fractions. What can I do with that 3/2 denominator? I can multiply it here by the reciprocal. So now what am I going to have? 1 over 27, right? 1 over 27 times u to the 3/2 integrated from 5 to 8. Because what I did is I said 2 will reduce the 18 into 9, and 3 times 9 is 27. That's what I did. Alright, so anyway, what you're going to get is, what did we say, 7.63? And so that is your arc length. I'll do it the regular way, that's fine. 1 over 27 times, you're going to have 9x minus 32 raised to the 3/2 integrated from 5 to 8. So you're going to have 1 over 27 times 9 times 8 minus 32 raised to the 3/2 minus 9 times 5 minus 32 raised to the 3/2. But what I did, right, what I did on the board over there is, instead of writing all this down, I just went ahead and substituted it into my boundary. But again, if that totally throws you off, don't do it. If you like the way you're doing it, then go for it. Okay? Any questions about this? Like I said, it's a lot of algebra.
You had a previous slide where you said, depending on if it's a function or not, where you get the boundaries, whether it's A over there, you get the B over here.
Mm-hmm.
If it's a problem, it is a function, so you're looking for X boundaries.
Which are going to be your X coordinates.
I just wrote it down with that.
Mm-hmm. And then on the if you're going to use the bottom one, which means you had to pretty much solve for X instead of Y, you're going to use your Y coordinates. Is that better? Anything else? Like I said, a lot of algebra, a lot of things that you have to think about. And I will give you a little bit of a hint. Instead of, a lot of you are thinking about busting things up. Instead of busting things up, consolidate. Try to consolidate. Because if you consolidate, it's going to help you with that radical. Okay. Let's try another one. Or not. Okay. Look. First thing I see when I look at this problem and I'm finding arc length, the first thing I see is this right here. That's nice. Yes? Y is already solved for you, so this is f of x. And I'm going to write it in functional notation because I'm about to have to take the derivative. Okay?
It's not under the radical.
Right, the one is not under the radical, so we're not, yes. All right, so we have 6 times x to the 2/3. Remember, your power is your numerator and your index is your denominator. That's always. Plus 1. So f prime of x. F prime of x is going to be 2/3 times 6, which is going to be what? 4. And then less than 2/3 by 1, which is going to be what? Negative 1/3. And then, of course, the derivative of 1 is 0, so we don't have to worry about that. Okay, so since we have y, which formula are we going to use? Arc length is equal to what? The integral? A to b or c to d? A to b, because y is solved for, so we have f of x, and if you'll go back and look, the actual formula tells you which one you're doing, because it's 1 plus f of x, or f prime of x, squared dx. So that's the one we're going to use. All right, so what are our boundaries? Always a to b. Negative 1 to negative 8. Always a to b. I know that sounds backwards, but it's always going to be a to b. Okay? 1 plus, and then we're going to take our derivative, and we're going to square it. All right, so let's start in on some algebra. What's the first thing you want to do? Yeah, we're going to square that derivative. That's going to be the first thing you want to do, square that derivative. So 4x to the negative 1/3 is going to be what? 16x to the negative 2/3? Yes. Okay, so we don't have a fraction this time, or do we? Yeah. You do have a fraction this time. So we're going to have the integral from negative 1 to negative 8, and I'm just going to rewrite it 1 plus 16 over x to the positive 2/3 dx. So how are we going to consolidate this one? How are we going to make one fraction out of this one? That 1's going to turn into what? x to the 2/3 over x to the 2/3, right? So you're going to have x to the 2/3 plus 16 over x to the 2/3. Okay, so let's try to get rid of that denominator. Watch this. I can say the square root, and I can write it as x to the 1/2 if I wanted to. X to the 2/3 plus 16 over, actually I think I am going to do that because I'm going to do it on the bottom anyway, so that would make sense. So let's do x to the 2/3 plus 16 to the 1/2 over x to the 2/3 to the 1/2. Now, going back to your algebra days, can I, in the numerator, because I have a group in the numerator, I have a sum or difference in the numerator, can I take x to the 2/3 to the 1/2 and 16 to the 1/2? Can I separate it out like that? Can I take those groups and do that? In other words, this is what I'm asking you. Is that going to be x squared plus 4? No. It's the same concept. You cannot do that. You cannot do that. So, the numerator is going to have to stay as is. So that's going to turn into the integral of -1 to -8. The numerator is going to have to stay as is, but the denominator, look at what we have. We don't have a group down there, do we? So the denominator is going to go to what? X to the 1/3. Now what did we do a while ago when we got here? When we got to this point, what did we do a while ago? Look back at the other problem and tell me what we did. No, we didn't integrate just yet. What did we do? We got rid of that denominator. How? We pulled the 1/2 out front. Yes? Do you remember that? Can I pull this x to the 1/3 out front? If anything that you learned this week, this should be something that you learned. I am taking the antiderivative with respect to x. So anything, whether it be a single term or a group that has x in it, has to stay in for integration. Okay? So I cannot take that x to the 1/3 out front because I'm integrating with respect to x. I'm finding the antiderivative with respect to x. So I need that x. So, crud. I don't know how to integrate a fraction. Go back to Cal 1. You know what to do. Anytime you had to integrate a fraction or anytime you had to integrate something to a power, what did you use? Watch this. U substitution. If I let u be x to the 2/3 plus 16, what is du? Aha. I can even rewrite that if I want to. That's going to be 2/3 over x to the 1/3. So there's that 1 over x to the 1/3. Do you see that? I don't need the, let's try to take the derivative. There we go. Get rid of that. We don't need that. So I need the x to the -1/3, right? Do I need the 2/3? I don't see a coefficient of 2/3 anywhere in my antiderivative. I don't see a coefficient of 2/3 anywhere in my integral. I see an exponent of 2/3, but I don't see a coefficient. So I don't need that 2/3. What do I do with it? I use a compensation, right? We compensate. Multiply by the reciprocal, which is going to be 3/2, and now you have the x to the -1/3. Watch this. Let's use a checkoff system, okay? When I do that antiderivative, or when I do that derivative, I have a dx, check. I let x to the 2/3 plus 16 be my u, check. And then and I can say that that's going to be 1 over x to the 1/3. Well, I can rewrite this if I want to. Check. So when I do the u substitution, I get everything I need. So we're good. We're good to go. Okay, so what are we going to do from here? Well, we're going to have 3 halves times the integral from -1 to -8, u to the 1/2 du. Can you integrate 1 to the u to the 1/2? Hopefully we've done it tonight already, yes? Go from here. What are we going to do? If I integrate u to the 1/2, what am I going to get? U to the 3 halves over 3 halves. And we're going to integrate from -1 to -8. So what do I do with that denominator of 3 halves? What are we going to do with it? We're going to bring it out here and we're going to multiply by the reciprocal, which is 2/3. What's going to happen? They're going to cancel. Isn't that wonderful? So now what I have is u to the 3 halves integrated from -1 to -8. Do this. Okay, if I do a change of boundaries, what I'm going to do is I'm going to take that -8 first and plug it in for u. So here, if I plug in -8, so we'll have -8, I can get something to write with, -8 to the 2/3 plus 16. Well, basically, the way I look at this is I say the cube root of -8, which is -2. If I take care of the denominator first. The cube root of -8 is -2, and then -2 squared is 4. So you get 4 plus 16, which is 20. And then if I take that -1 and I plug it in, the cube root of -1 is -1. -1 squared is going to be 1. And that's going to be 17. So, why would you do that? Well, to me, it's just easier to write. It's a little bit shorter, I guess, to do this. U to the 3 halves, and my new boundaries are going to be from 20 to 17, or 17 to 20. So, you're going to do 20 to the 3 halves minus 17 to the 3 halves. And you can put that straight in the calculator. You can do 20 caret key 3 fraction 2 minus 17 caret key 3 fraction 2. Either way, you should come up with approximately, not exactly, approximately 19.35. You might want to use parentheses, but it won't do the negative coefficient. Let's try one more. Let's try this trig one. No comments. Okay. So, again, when I look at this problem, what's the first thing you see? What do you see? It's already solved for y for you. Okay? Since it's already solved for y, we know that f of x is the natural log of cosine x. Okay? So, in knowing that, what does that tell me? Well, it tells me which formula I'm going to use on my formulas page. That's what it tells me. Okay, so I need the derivative. You may want to pull out your derivative page from Cal 1. What is the derivative of ln u? Because that's what I'm looking at. 1 over u. Finish it up. 1 over u du. 1 over u times the derivative of u. What's the derivative of cosine x? Negative sine x. Okay. And we can put that together. For you trig masters, tell me what negative sine x over cosine x is. Tangent x. Negative tangent x. Very good.
Crazy how much I remember.
That simple trig's fun. Okay, and I love this problem because y'all think trig is just absolutely horrible. Watch this. Trig's a lot better than the algebra that we've been doing. Watch. What are our boundaries? They didn't even give you ordered pairs because in trig we don't have ordered pairs. What are your boundaries? It straight up tells you 0 to pi over 4. Watch this. 1 plus negative tangent x squared dx. Clean that up a little bit. What's that going to be? What happens when I square negative tangent x? I get positive tangent squared x. Right? Negative times negative is positive. That's always. Tangent x squared is tangent squared x. So that's cleaned up.
Could you go a step further?
For those of you who know your Pythagoreans, 1 plus tangent squared x is the same as what? Secant squared x. So you have from 0 to pi over 4 times the square root of secant squared x dx. Very good. All of that is on that trig page that you got in Cal 1. Every single bit of it. The sine over cosine is tangent. That's on there. The 1 plus tangent squared x is your Pythagorean identity. It's on there. Okay, so let's talk about some algebra a little bit. What happens when you square root a square? They cancel each other out. So what do you think is the square root of secant squared x? Secant. So we have the integral from 0 to pi over 4 of simply secant x dx. Okay, and I'll be honest with you, I don't know this one, but I know how to find it. Let's see if you know how to find it. Get your formulas page out or look at the inside front cover of your book, either way. And tell me what the integral of secant u du is. What is the integral of secant u du? Not secant squared u, secant u. Natural log. Good. Of secant x plus tangent x plus your constant, which we don't need because we have a definite integral, right? Well, and I just took the integration. So we're going to integrate that from 0 to pi over 4.
Why do you switch it off?
Because the integral, the antiderivative of secant x is the natural log. So actually, when I write down the natural log of secant x tangent x, I actually took the antiderivative. So the antiderivative symbol goes away.
I mean, your boundaries switching from the left to the right, that because let yourself know you get the integral
It's just
already?
notation. It's just a way for me to get rid of the integral symbol. Okay, this goes to the not so fun part, the part that y'all don't like. But you have that chart on the inside back cover of your book, which you should have copied onto your formulas page somewhere, okay? So get that chart out, and as I'm writing, start looking for secant of pi over 4, tangent of pi over 4, secant of 0, and tangent of 0. Start looking for those, because that's what you're going to do. You're going to have the natural log of secant of pi over 4 plus tangent pi over 4 minus the natural log of secant of 0 plus tangent of 0. Whoa. So, natural log. What is secant of pi over 4? You got it yet? I don't want a degree, I want a number. What is secant of pi over 4? Square root of 2. What is tangent of pi over 4? 1. Minus the natural log. What is secant of 0? And what is tangent of 0? 0. So what I have here is the natural log of the square root of 2 plus 1 minus the natural log of 1. Well, you can plug this straight in your calculator. I mean, there is some more algebra that we can do here, but you can plug it straight in your calculator. If you do natural log, and my calculator gives me a parenthesis button already, just do the natural log, radical 2 plus 1, make sure you close that parenthesis before you move on. Minus, and then you can do natural log of 1 also, and put that in your calculator. Either way, what are you coming up with? And 0.88 is sufficient. Make sure you can come up with that number in your calculator. And that is arc length. What do you think? It's not that bad. There's a lot of algebra, so you're just going to have to be careful with your algebra. And then the trig ones are honestly not that bad either. Okay. Yeah, I mean, I wouldn't say always they're going to do that. You can always hope that they're going to do that, but I wouldn't say. Well, the thing about it is, Patrick, and I agree with you. The thing about it is this: either one, they're going to simplify down to an integral that you have on your integral sheet that I gave you in Cal 1, or 2, you're going to be able to do a U substitution, which is something that y'all learned in Cal 1 also. So just keep that in mind. Either one, if you're going to have a straight up integration from your formulas page, or 2, you'll have to use a U substitution. Either way, though, you're right. Okay. So this is arc length. Okay, 2-dimensional arc length. So, let's see, on your formulas page, on your formulas page, I want you to write these down. This is surface area, or surface of a revolution. Basically, it is surface area. Put these somewhere on your formulas page. They're not on there, but I certainly want you to have them on there. You can call it surfaces of revolution, or you can call it surface area, however you want to look at it. So S is going to be your surface of revolution. It's going to be your surface area. Usually the problems are going to look like this. It's going to say find the area of the surface. Well, in geometry, that was find the surface area. Same thing. Same thing. So I want you to compare this formula with the formula that you just did. Notice that you have 2 pi. That's only because we're going to 3D now. So notice that you have 2 pi times your function. That is the rotation of your function. Because from 0 to 2 pi is a full rotation. That's where the 2 pi comes into play. And you're taking that full rotation times your function that you're actually rotating. So that's why you have the 2 pi times f of x. Boundaries are the same. If you're going with respect to dx, then you're going to find boundaries on your x-axis. dy, you're going to have boundaries on your y-axis. And then you have, again, same thing that we just did, the square root of. So that's times. You have 2 pi times your function times the square root of 1 plus your derivative squared. Okay? So the only thing we're doing is we're adding the products, or the factors, of 2 pi fx. 2 pi f of x. Okay? So that's your surface area. Not too much different at all. So let's look at this. Find the area of the surface generated by revolving the graph. And when I look at this, again, this is what I see. I see y. So I see f of x. And I know in my formula, remember your formula? Your s, please don't confuse that with your integral symbol. That's an s. Let's see if I can do it a little bit better. S, is that better? S is equal to the integral. For this one, it's going to be a to b, because we do have f of x. A to b, and then you have 2 pi f of x times the square root of 1 plus your original formula that we were using a while ago, f prime of x squared dx. So there's your formula that you're going to use. All right, so we know that we need the derivative. So f prime of x is going to be what? 3x squared dx, of course. Can you tell what that is? Okay, so you have 3x squared. Now, let's go here. What are our boundaries? 1 to 2. And I'm just going to, for this first one, I'm just going to plug straight in, okay? So 2 pi is 2 pi. It's not going to change. It's a number. It's 2 times 3.14. It's a number. So you can imagine what I'm going to do with that, right? What do you do with all constants that have nothing to do with an x? You're going to pull it out front. Okay, so we have 2 pi times our original function, which is x cubed, times the square root of 1 plus my derivative squared, and then of course the dx. Okay, so all kinds of things that we can do here. Let's start by taking that 2 pi out of the way. It is a constant. That's what allows me to bring it out. And then let's rewrite this. You're going to have x to the third times the square root. If you want to put both of them in parentheses, it doesn't matter. 1 plus, let's do this algebra here. So we're going to have what? 9x to the fourth. Well, you know what I want to do. You're going to have 2 pi, probably the same thing you want to do. And if you had have done it in that previous step, that would be fine. What do I want to do here? Snotty poo-poos. Put that on pause. Why didn't y'all tell me that was on pause? Sorry. And I have no idea how long it's been on pause. Frank, I apologize. Okay. Yep, it will. From whenever I paused it to right then, and I don't know. Questions? So surface area is not that bad. Surface area and arc length, or area of surface, whatever, and arc length, not that bad. It's a lot of algebra, but it's not that bad. Okay, I think we will just pick up here